Now we are ready to do some calculations that will allow us to do practical laboratory work. What I mean is, we have our balanced equations, and the balanced equation tell us the exact quantities of reactants needed and the amount of products that will be produced based on the amount of reactants we use. And so we can do work in the laboratory where we can set up our reactions where we aim to produce a certain amount of product, and based on what our aim is, we can start with a certain amount of reactants. So we learned about the chemical equation. Not only that, but we learned that we must balance the equation. If I say that hydrogen gas and oxygen gas react to produce water, I can write it as H2 plus O2 giving us H2O, but that would not be balanced. We must balance a chemical equation by putting coefficients before the um, formulas of each of the reactant and the product, and the coefficients are whole numbers. We learned how to balance chemical equations. So here is the balanced version of that equation of hydrogen gas and oxygen gas reacting to produce water. It says 2 moles of H2 react with 1 mole of O2 to produce 2 moles of H2O. That's a balanced equation. All the number of hydrogen atoms on the left are balanced with the number of hydrogen atoms on the right. All the number of oxygen atoms on the left are balanced with the number of oxygen atoms on the right. Once we have a balanced equation, we are ready to do further calculations that will enable us to do some practical work in the lab. So, what kind of practical work? Well, let's say that you start with 4 moles of H2 instead of 2 moles of H2 because you have more than 2, and you want to use 4 moles. How many moles of oxygen is needed to react with 4 moles of H2? That's a valid question because 2 moles requires 1 mole of H2, then 4 moles requires how many? And some of you may easily guess the right answer in your head. If 2 requires 1, 4 should require 2. But we will do it scientifically using conversion factors because eventually it will get more complex that it won't be easy to just come up with the answer in your head. The conversion factor that we will come up with will be based on the coefficients here. 2H2 for 1O2. And every time we have a reaction in which we have to do this kind of calculation from the balanced equation, there will only be two reaction species at a time that we will have to consider. Either two reactants, such as if you have X amount of one reactant, how much amount of the other reactant you need. So you have reactant A and reactant B. A is the amount given and B is the one you don't have. Or something like just the products. If you had two products, if you produce X amount of A, what's the amount of B you would produce at the same time? So in that case, we are sticking with two products, or one could be a reactant and one could be a product, such as if you react 3 moles of H2, how many moles of H2O you would make? In that case, this is your A, H2, and this is your B. And it doesn't have to be that the reactant has to be A and the product has to be B. And I'm just coming up with the alphabet A and B just to designate what we are given as being A and what we are trying to find as being B. You could be given A here, that you produce 7 moles of H2O. How many moles of O2 were used? In that case, H2O is A and O2 is B. Okay. So in this case, my A is H2 and O2 is B. I start with 4 moles of H2. How many moles of O2 are required? So that's our balanced equation. And here is another question similar to that. How many moles of O2 are needed to react with 4.26 moles of H2? Now we need to put our pen on paper and solve this because we can do this in our head. But notice how again we just are looking at two things. H2, the amount is given, so let's call it A, and the moles of O2, the amount we are trying to find, so let's call it B. And so the conversion factor is obtained from the coefficients. The coefficients for H2 is 2, and that 2 here represents 2 moles of H2, and the coefficient for O2 is 1. Remember, when there is nothing here, that means there is a 1 mole of O2. So 4.26 moles of H2 is what we started with when we were given that information here. How many moles of O2 are needed to react with 4.26 moles of H2? Multiply that with our coefficient based conversion factors. And you have to set it up where your denominator term cancels out with your starting term. And that's why you need to specify moles of what. Only then can you figure out what cancels out, because moles of H2 can only cancel out with moles of H2, not with moles of O2. So here you put the moles of H2 in the denominator and the moles of O2 in the numerator. And once the moles of H2 cancel out, the unit that remains is moles of O2 in the answer. And just like you have been doing previously, you then do your calculation in a calculator, and you must set it up correctly using parentheses, and then the answer must have the right number of significant figures. The coefficients here, which are used as numbers here, are exact numbers, so do not count any sig figs in them. And the answer to this question then is 4.26 moles of H2 requires 2.13 moles of O2 in order for this reaction to happen. What happens if you have less than 2.13 moles of O2? Perhaps you have an oxygen tank and a hydrogen gas tank. Your hydrogen gas tank contains 4.26 moles of H2, but your oxygen gas tank contains less than 2.13 moles of H2. When that happens, some of the H2 will be left over, because only when you have 2.13 moles of O2 can all the H2 react. If you have less than that, then some of this will be left over. What happens when you have more of this? So instead of 4.26, you have 5 moles of this. And well, what if you have more of this? Instead of 2.13 moles, you have 3 moles of this. Then who will be left over? Then O2 will be left over. We will develop something out of that when you don't have the exact amounts to completely react with each other, the exact amount of reactants. But so far in this example, we are saying that 4.26 moles of H2 requires exactly 2.13 moles of O2 to completely react and be gone at the end of the reaction. So this is how we find out the moles of our B, our destination in terms of starting with at A and going to B, using the balanced equation coefficients and making a conversion factor out of them.